We have guided problem solving related to the topic binary vapor power cycle. So we're given here with a 100 megawatt combined gas steam power cycle. The topping cycle is a gas turbine cycle that has a pressure ratio of 8. Air enters the compressor at 300 Kelvin and the turbine at 1300 Kelvin. The isentropic efficiency of the compressor is 80% and that of the gas turbine is 85%. So we need to use this efficiency later on to get the actual value of enthalpy at the points. The bottoming cycle is a simple ideal Rankine cycle, as you can see here. A simple ideal Rankine cycle operating between the pressure limits of 7 megapascal and 5 kPa. The steam is heated in the heat exchanger by the exhaust gases to a temperature of 500 degrees Celsius. So the steam here is heated to 500 degrees Celsius. That's why we have here 500 degrees Celsius at the entrance of the turbine. The exhaust gases leaves the heat exchanger at 450 Kelvin. So it refers to the temperature at 0.5. So it leaves the heat exchanger at 450 Kelvin. So we need to determine the ratio of mass flow rates of steam and the combustion gases. Determine the total neat work output per kilogram of combustion gases. Determine the mass flow rate of combustion gases and determine the mass flow rate of steam and the thermal efficiency of the combined cycle. So first, we need to get the value of the enthalpies of the gas turbine or the Brayton cycle. So we switch our attention to the topping part, which is the gas cycle. So air enters the compressor at point 1. We have here 1 prime so that we will not be confused with the Rankine cycle. So we have 1 prime, 2 prime, 3 prime, 4 prime, and 5 prime. So it is given that at point 1, air enters at 300 Kelvin. So that's why we have here, it's actually 300 Kelvin here. So we have here 300 Kelvin enters the point 1 of the gas cycle as 300 Kelvin. So we can get the enthalpy using the table 17. So that is the ideal gas properties of air. So H1 prime is equals to the enthalpy at 300 Kelvin. From the table, that is 300.98 kilojoules per kilogram. So after that, you need to get the Prandtl number at 300 Kelvin also, and that is 1.386. We will use this Prandtl number to get the enthalpy at 0.2 after leaving the compressor. So for the Prandtl number at 0.2, so this is actually an isentropic process. As you can see, 1 to 2 is an isentropic process. So this is the compression. So the pressure ratio is given in the problem. So that's why we can use that pressure ratio. That's the ratio of the pressure at 0.2 to the pressure at 0.1. And that is also equals to the Prandtl number at 0.2 to the Prandtl number at 0.1. That's why we got the Prandtl number also at 0.1. So from the pressure ratio, which is given as 8, so we just get the PR2. We multiply it with PR1 from state 1, and that is 11.10. So we can use this 11.10 to get the enthalpy at 0.2. So the enthalpy at 0.2 is the enthalpy at PR2, which is 11.10. So the enthalpy is 544.35 kilojoules per kilogram. So this is the enthalpy here at 2. But since we have an isentropic efficiency for compressor, that's why it deviates to 2 prime. So what we got here is 2, not the 2 prime yet. So this is how we get the value of the Prandtl number at 0.1. As you can see here, we have the temperatures, enthalpy, and the Prandtl number. So we're given with the temperature of 300 Kelvin. That's why we have enthalpy of 300.19, and the Prandtl number here is this one. On the other hand, at 0.2, we use the Prandtl number 11.10 to get the enthalpy. This one is the enthalpy, and then the temperature and the enthalpy. Next is to determine the enthalpy at 3 prime. So this is after the combustion chamber. So now you added heat here by the combustion of fuel, for example, to heat it farther to 0.3. As you can see, there is an increase of heat now from 2 to 3 prime. So we can get that since 3 prime is given, that's 1300 Kelvin. So H3 prime is just enthalpy at 1300 Kelvin, and that is this one using the table. We also need to get PR3 again so that we can get PR4. So PR3 is the Prandtl number at 1300 Kelvin, and that is 330.9. So since the same pressure ratio is actually in 3 and 4, that's why we can still use this pressure ratio, but this time it's P3 over P4. It's equals to RP. The same also with the Prandtl number P3, PR3, and PR4. So substituting PR3, which is 330.9, and the pressure ratio is 8. So PR4 is 41.36. So we can use this PR4 to get the enthalpy of the gas that leaves the gas turbine. So H4 is enthalpy at PR4, and that is 789.37 kilojoules per kilogram. So now we have the value of enthalpy at 1 prime, at 2, 3 prime, and the enthalpy at 4. Take note that there's an isentropic efficiency given for the gas turbine and the compressor. That's why we need to get it later on. That's the real 4 prime and the real 2 prime. That's why here it's not actually prime, but it's the as is. So this is how we get the value at 0.3 using the table. Same also with 0.4. So take note that if the value is not found in the table, you can use interpolation. For the enthalpy at 0.5. So the enthalpy at 0.5, so 0.5 is given. Based on the problem, it leaves the heat exchanger. So the exhaust gas, it exchanges heat here, and it leaves the heat exchanger at 0.5, 5 prime, as 450 Kelvin. So that's why we use also the table to get enthalpy at 5 prime, and that is 451.8 kilojoules per kilogram. So this is how we use the table to get the enthalpy at the 450 Kelvin, that's 451.8. So we have here 451.8 kilojoules per kilogram. So now that we have those enthalpies, we can get the actual enthalpy here because we have an actual process here. There are isentropic efficiencies given. So the isentropic efficiency of the compressor is 80%. So meaning it's not a perfect process. That's why we need to get the actual value. And the isentropic efficiency of the compressor is work isentropic over work actual, and that is equals to H2 minus H1 prime divided by H2 prime minus H1 prime. So the actual is the H2 prime minus H1 prime, and the isentropic is the H2 minus H1 prime. That's why we have it here. So we need to solve for 2 prime. So we need to solve for 2 prime. And since we already have 1 prime in the calculation and the isentropic efficiency of the compressor is given in the problem, so H2 prime is 605.39. So the actual enthalpy leaving the compressor is 2 prime, and that is 605.39 kilojoules per kilogram because of the isentropic efficiency. Also in the turbine, it's also given as 85% for the gas turbine. So it's not actually 4, but it's 4 prime that leads the turbine because of the isentropic efficiency. So for the turbine, the isentropic efficiency is work actual over work isentropic. So the actual work is actually this longer path, this path here, the shorter path, which is H3 prime minus H4 prime, divided by the longer path of the straight or isentropic process, H3 prime minus H4. So we need to solve for the actual form. So H4 prime is 880.36 kilojoules per kilogram. So now that we have already the enthalpies, so we summarize all of those enthalpies. So we have H1 prime, H2 prime, H3 prime, H4 prime, and H5 prime. As you can see, the greatest should be H3 prime because this is the exit of the after the addition of heat. So we can determine first the power input in the combustion chamber, and that is our Q in. So as you can see, it's the difference of the enthalpy at 0.3 and 2. So this is the Q in here. So Q in is H3 prime minus H2 prime, and that is equals to 790.58 kilojoules per kilogram gas. So take note that gas flows here. That's why we use here per kilogram of gas. So it's actually the heat that you added in the entire system to run the entire system is 790.58 kilojoules per kilogram of the gas. For the compressor work of the gas cycle, that is equals to the change of all the difference also of the enthalpies here, and that is H2 prime minus H1 prime. And that is 305.2 kilojoules per kilogram gas. For the gas turbine work, that is H3 prime minus H4 prime. So this one, the expansion here. So the turbine gas work is 505.61. So the work net of the gas turbine cycle, so for the gas turbine cycle, the work net is work of the gas turbine minus work of the compressor. And that is equals to 210.41 kilojoules per kilogram gas. So meaning we can produce 210.41 kilojoules per 1 kilogram of gas. So now that we already have the data for the gas cycle, now we will proceed to the steam cycle or the Rankine cycle. So we just have here a simple Rankine cycle at the bottom. So we just fill in the table using our previous knowledge of simple Rankine cycle. So we have point 1 is actually saturated liquid entering the pump. We're given with a pressure of 5 kPa here. So we can readily get the values. 1 to 2 is isentropic process, as you can see here. So they have the same entropy. And since this is subcooled, we just use pressure and entropy to get the temperature and enthalpy at point 2. At point 3, we're given with pressure and temperature. So that's 7,500. So we just use the specified state points for RefRup, our steam table. So we have entropy and enthalpy. And for the mixture, since 3 to 4 is isentropic process, you have the same entropy. And using the entropy and pressure, we can get the temperature and enthalpy of the steam. So take note, this one is steam, the steam cycle. So we just use the simple Rankine cycle that we already tackled in the topic number 2. Topic number 1 or 2, I think. So for the steam cycle, we also need to get the work net. So first, for the work of the pump, that's just H2 minus H1. So that's 7.02 per kilogram steam. So this time steam is flowing here. For the turbine work, that is H3 minus H4, and that is 3411.4 minus 2073. So the work of the steam turbine is 1,338.4 kilojoules per kilogram of steam. So the work net for the steam turbine cycle is work of the turbine minus work of the pump. And that is 1,331.38 kilojoules per kilogram steam. So we already have the work net for the gas cycle and the work net for the steam cycle. We will use that data to get the first unknown, which is the ratio of the mass flow rate of the steam and the combustion gases. So this refers to the ratio of the mass flow rate of the steam in the steam cycle and the mass of the gas flow in the gas cycle. So to get that, we need to use energy balance at the heat exchanger. So we do energy balance at the heat exchanger. So we're given already with the enthalpies at the different points. So using energy balance at the heat exchanger, this is the heat exchanger. So the energy entering are zero point 0.4 and zero point 0.2, as you can see here. But take note that 0.4 is a gas, 0.2 is a steam. That's why we have here mass of the gas times H4 prime plus this 0.2 here, which is a steam, so mass of the steam times enthalpy at 0.2 equals to the energy leaving, which are 5 and 3. The arrow here represents its leaving. The flow is leaving the heat exchanger. So we have M gas H5 prime plus mass of the steam at 0.3 times the enthalpy at 0.3. So what happens in the heat exchanger is that the exhaust gases in the gas cycle boils the water to produce steam. So that's why it's called heat exchanger, because there's a heat exchange between the gas and the steam. If we are going to rearrange that, so we group together those that contains Mg and Ms so that we can get the ratio of the mass flow rate of the steam and the combustion gases. So we already have that enthalpies. We tabulated it here again, so that Ms over Mg is equals to this one. So now that we have these values, we can get now the unknown, the ratio of the mass flow rate of the steam and the combustion gases. So that's 0.1312 kilogram steam per kilogram gas. The next is the total network output per kilogram of the combustion gas. So here we are to determine the total network output. So since we have two turbines, we have the gas turbine and the steam turbine, we need to add this one, but this time we need to get the value in terms of per kilogram of the combustion gas, meaning per kilogram of gas, or mg. So our work net is actually the per kilogram of gas. So that's actually the work net of the gas turbine. So the work net of this gas cycle here, plus the work net of the steam turbine or the steam cycle, because we have to deduct also the pump work and the compressor work. So that's why it's net, multiplied by the ratio of the masses. As you can see here, we can actually cancel out mass of the steam, so that what remains here is mass of the gas. So if we substitute the value, so the mass that we can actually see here, that we can cancel out the kilogram steam, so that the result is per kilogram of the gas, which is also the requirement. So the work net is 385 kilojoules per kilogram of gas. C is the mass flow rate of the combustion gases. We're given with a work net of 100 megawatt. So the work net here refers to the total work net of the entire system. So the work net is equal to mass of the gas per work net based on the gas. And since we already have the work net, that's 100 megawatt or 100,000 kilojoules per kilogram, and the work net of the gas per kilogram gas, which is 385. So the mass of the gas is actually 259.7 kilogram gas per second. So that's a huge amount of gas needed. That's 260 kilogram per second of gas. Next is the mass flow rate of steam. So we just use the ratio to get the steam, the mass of the steam. We multiply it with the mass of the gas so that we can cancel out kilogram gas. So we cancel out kilogram gas. So the mass of the steam is 34 kilogram of steam per second. So if we have 259.7 kilogram gas, we can produce 34 kilogram of steam. And finally, for the thermal efficiency of the combined cycle, that is just equals to our work net over Q in. So take note that they should be in the same dimension, which is kilogram gas. So our work in, we got it already as Q in, that's 385, that's 790 rather, and our work net is 385 kilojoules per kilogram gas. So that's why our thermal efficiency is 48.7%. So that's how we analyze our combined gas steam cycle.